Good evening, guys. We are in the week 4 session of the course Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. And the week 4 is about modeling techniques and model validation using MATLAB. So and this is the week 4 or fourth practice session of this course. So let me share my screen. Is my screen visible? Hello. Can anyone please confirm? Hello.
Yes, sir.
Okay. So then we can start. So
Yes, it is visible.
okay. Thanks. So I am Teja Golla, a third-year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, Electrical Engineering Department, IIT Kharagpur. So the week 4 of this course is about modeling techniques and model validation using MATLAB. So just to summarize what we have discussed in the last week, which is week 3. So week 3 is about MATLAB custom model development and digital control. So in the week 3, whatever we have discussed, it is about analog control. So let me select the pen. So first I have shown the analog control model, MATLAB model development. So I have shown the simulations, live simulations of voltage mode control and then peak current mode control and constant on time and constant off time, and why minimum on time is required and why minimum off time is required and how to implement them. All the logics we have discussed. And after that, I have shown the digital PID controller, what are the equations of the digital PID controller and how to implement it in the MATLAB. Then we moved into the digital controller after this. So in the digital controller, I have explained the architectures followed by MATLAB model development. So first, I have shown the digital voltage mode control, and in current mode control, we have done the mixed signal, but I didn't get time for fully digital. So if you want me to discuss today, then I can discuss today. So I have added it in the slides. So if you want me to quickly show the simulations of fully digital, then we can do it today. Or if you want me to skip, I can skip. So it's up to you. And in constant on time and constant off time current mode control, first I have shown the MATLAB model development, and then followed by why we need minimum on time and minimum off time. So I have shown it in the simulation, and how to implement minimum on time and minimum off time. What is the logic behind the implementation of that, and how we are implementing that in the MATLAB. So that we have rigorously discussed, and followed by hysteresis current mode control, peak, valley, and average. And we have solved few problems as well. So we have solved problems on the architecture and how to get all the information if some screenshot of an architecture is given or some screenshot of a MATLAB simulation is given. I have told how to extract the data, whether it is fixed frequency, variable frequency, constant on time, constant off time, whether it is minimum on time block or minimum off time block. If so, what is the off time? What is the minimum on time? So all these things we have discussed in the last week section. So just to summarize still here. So week 1, it is a basic introduction, and week 2 is all about different modeling techniques as well as different sampling methods, and week 3 is all about implementing the same using MATLAB model development, and week 4 is all about the different modeling techniques and validating. So if we want to design a controller, so next week is all about controller designing. So before we dive into controller designing part, so what models or what small signal models can we consider it? How much are they reliable? So do they deviate from the actual model? Is there any validity issue, or to what extent can we use, and what are the different modeling techniques that are available? So all those things we'll be discussing, and we'll discuss something called large signal signal tuning. So I'll come to that point. So actually last week some people have asked me for the MATLAB simulation. So some people have asked, sir, if you can give me the MATLAB files, then it would be easy for you to simulate. So I have talked with this SAR as well regarding the same, but actually due to some issues, we cannot share the MATLAB files, but that does not mean that you have to do it by yourself. So we will be providing you all the materials that you need to do the MATLAB simulation. So, and I will be there to help you. Also, SAR will be taking one live session in YouTube in this month. So by the end of this August month, SAR will be taking one live session. So I will be there to help you in MATLAB simulation, but we want you to do it by yourself. So if you are stuck at any point, you can either contact me, or you can post it in the forum, course forum, or in the upcoming week, or maybe this week, SAR will take a live session. and it will be informed to you by NPTEL people. And in that during that live session also you can ask sir. But we want you to implement the MATLAB simulation, and sir has discussed. So to start with, so you follow this method. So in lecture 11 of the previous course, so I have embedded the link in the text. So link is available here. So when I share this PDF document, you go through this lecture. So here sir has shown the script how to link code with Simulink, all the basic blocks, and sir has done everything from scratch. So you can play the video, and in parallel you can do the simulation. So code with Simulink as well as open loop, how to make a open loop buck converter in MATLAB, sir has shown. So if you this is 1 hour lecture, if you actually watch this video, you'll be able to develop till open loop. So you can make a MATLAB model of open loop buck converter, and you can run it only by looking in this lecture. And after this lecture, you can go through the lecture 12 of the same course, and again the link is embedded here. So you can directly click this, and it will take you to that YouTube video. So this is the same thing. So extension of this. So sir has considered analog voltage board control, I guess. So until this point, you can actually, by looking at these videos only, you can make the MATLAB model until analog voltage board control. So after that, by making slight changes, by replacing ramp with the inductor current, you can make mixed or analog current mode control. So until this point, it would be easy for you. So after that, if you want to do constant on time, constant off time, you have to see a few more videos of sir in the same course. So that you can do, but I believe everyone will be capable enough to do until this point. So using these 2 videos, you can do until this point. So if you want to do, then in this course, in the last week, lecture number 21, I have also shown the MATLAB simulation case study. So sir has done a recap of voltage and current mode control implementation using MATLAB. So sir has considered voltage mode control, current mode control, constant on time, constant off time. So sir has shown it in live. So you can also refer to this video, and you can make all the analog control techniques in MATLAB. So all analog controls can be implemented in MATLAB. So up to this point, you can make analog control. So I want you to try. I don't know how many students have tried till this point, but if you have not tried, I request you to try. You can just start it because if we give you MATLAB models, then you will just simply run it, and if you face any issue, you will not be able to debug it. You will not be able to understand all the blocks. But I'm sure that you will be facing issue. Maybe you're afraid that who will help you. I am there. I'll be there to help you. So you can mail me anytime, or you can ask me in these sessions also, or you can ask in the forum. So the TAs are very active, and they'll reply your queries. Also, you can ask sir. So sir will be taking one YouTube live session this month. So you can ask sir. So we are always there to help you. So until this point, you can implement all analog controls in MATLAB. So after this, you have to go through these lectures. So sir has first discussed about basic digital control box. So how to implement ADC, how to implement controller G of Z in digital in MATLAB. So sir has discussed. So until this point, if you can complete it in the MATLAB, then the actual control architecture is nothing but some modification of this and this. So you have to replace analog control MATLAB model by a few blocks of ADC and the controller, and I'll be there, so don't be afraid. So we are there to help you, but we want you to start. So has anyone tried solving this? Has anyone started trying to implement in the MATLAB? Has anyone tried? Okay, but have you gone through last week's NPTEL lectures, the entire week from 21 to 20, 21 to 30?
Yes.
Okay.
Yes.
And you have understood the concept, right? Yeah. Okay.
Yes.
Yes, sir.
But okay.
All the controllers we are not. I have not implemented some the buck converter and some initial voltage mode control. Those things I have implemented.
Okay. And if others, if you have not started, I request you to also start and do, and maybe you will be stuck at some point. So at that time, you can contact any one of us, sir or me or the TS, and we'll be there to help you. But we want you to start. And when you do this, then you will understand more. So you'll know if you face any issue, how to debug it. So all those things you will be knowing, and you'll understand each and individual blocks in a better way. So this is all about MATLAB simulation. So we are not providing any MATLAB models, but we will be there to help. So coming to week 4, which is modeling techniques and model validation using MATLAB. So the outline is as follows. First, I'll be discussing about small signal block diagram under digital control. So I'll be discussing about what is small signal block diagram under digital control. How is it different from analog control? Analog versus digital. What is the difference between small signal block diagram in analog and digital? What additional blocks will come? All those things we'll be discussing. And then I'll discuss about current loop stability analysis. So in the case of mixed signal, what is the current loop stability? What is the condition? And fully digital, what is the condition? So when I discuss this part fully digital, if you want, I can show the MATLAB simulation quickly, else we can skip that part. And then I will discuss about something called large signal DT modeling. So what is large signal DT modeling? What is the mathematical analysis behind this? And we'll also do some MATLAB simulation, and we'll compare this large signal DT modeling with switch simulation. So how good it is matching? All those things we'll consider in this particular discussion. And then from small signal, from large signal, we'll derive something called small signal DT modeling, and it has 2 methods, method 1 as well as method 2. So I'll discuss both the methods briefly. And then from the small signal DT modeling, we'll derive something called small signal transfer function. So why do we need small signal transfer functions for controller design? So using this small signal transfer function, we'll go to controller design part, which will be in the next week. So this entire week is just a building block connecting the architectures that we have learned in the previous week with the controller design that we'll be learning in the next week. So it acts like a bridge between these 2 weeks, and what all concepts that we require are already taught in this week by sir. So, and after this, we'll discuss about some stability aspects and loop transfer functions. So using the DT modeling, all the DT models that we have developed. So if I want to get some stability understanding or some to know whether the system is stable, say digital voltage mode control or mixed signal current mode control, how to do this using these derived models. And for the loop, why do we need loop transfer function? To design the controller to achieve a particular bandwidth as well as phase budget. So to check whether the actual loop is achieving this or not, we'll check. So for that, we need loop transfer function. And how do we arrive at this question? All these things we can discuss. And then we are considering different models. One is the continuous time, CT means continuous time, and the other one is continuous time with delay, and the other one is discrete time. So how accurate are these models? Which models we need to consider for controller design? So why we have so many models? What are the limitations of each model, and which one we'll be using for controller design? All this we'll be discussing, and then we can solve a few problems. So like if you want me to skip any part, maybe you can inform me so that I can skip parts and we can go to the next part. So the first part is a small signal block diagram. So again, it has 2 methods. One is the approximate, CT means continuous time. So CT means continuous time approach, and this is alternative approach. So before I start, I just wanted to ask, like, is this a good idea to discuss all the concepts before and then do problem solving, or do you want me to only solve problems for the 2 hours? Which one would be a good idea according to you?
So at last we can solve the problem, so that would be better.
Okay, so yeah, then I think I will go with this. I'll quickly summarize the things. If you have any queries, then we can have discussion followed by problem session. So to start with this small signal block diagram. So we have small signal block diagram in the digital domain. So I'll start from this point. So V sampled means it is nothing but V naught sampled voltage. So this is the output V naught that we are getting. So this is some sensor, and sensor has some gain, right? So that gain multiplied by H will get H into V naught. This is small signal, so that's why tilde. So this is just a perturbation. Because it is small signal, everything is perturbed around the steady state value. So it is small signal perturbation we call. So HV0 and then using ADC. So first we are multiplying with sensor. So we'll use a sensor to reduce the output voltage within the range of ADC. So we can consider this as ADC. And now it is being sampled, which gives the sampled output voltage subtracted from the reference, giving us V error N. So this is V error N. Now again it is in digital, right? Till here it is in analog domain. So now it is in digital domain. So a reference can also be inside the FPGA. So this will be in FPGA. So now we got error voltage going into the controller, digital controller.
Sir,
Yes.
sir, small signal, which means we are already assuming the it has reached the steady state.
Yes, yes. So around the steady state, we are designing. So everywhere when we design the controller using transfer functions, say transfer functions, whenever you are using transfer functions, those are small signal transfer functions. So those are perturbed small signal transfer functions. When you say GVD of S or GVG of S, these are all small signal. And this controller design is called small signal based controller design. Small signal based controller design. So this is small signal, right? We are getting this across the or around the steady state, and using that we are designing the controller. So now you may ask me, what is large signal based controller? So we will not consider any approximation. We'll consider the actual trajectory. So sir will be discussing in the upcoming weeks. So what is large signal tuning versus small signal tuning? So what is the improvement and how much it will be improved? So what are the advantages of going into large signal? What are the limitations of small signal? That sir will be discussed. So currently we are working with the small signal. This is the digital control. Yes, yes.
So large signal means we are considering both the transient part as well as steady state part.
Yes, yes, yes. So when we do small signal, we assume that it is around the steady state. But in the case of large signal, it does not have to be that. So during transient, so actual transient, how the inductor current and voltage is changing, that you will consider. So sir will show the trajectory of that IL and V0, and using that we'll consider, and based on that we'll design. It is a bit complex, but at that point, during that week, we can discuss on how to design controller using large signal based tuning. So now we got controller output VC of N, and we are holding it, right? So this is a zero order one. So we are holding that value for one cycle. And then this is the PWM. So in the case, like, you can consider this as a modulator gain. So in the case of voltage mode control, it will be 1 by VM or FM in voltage mode control. Sorry. I think someone has unmuted. Okay. So after this, some delay is there, right? So this delay, we can say modulator delay or sampling delay. So this tau d is the delay, total delay. And this gives D perturb, duty ratio perturb. And now it is input to GVD of S. So what is GVD of S? Control to output. Control to output transfer function. So now it goes into GVD of S. Again, it is in S domain. Now it will give V0 perturb. So this will complete the small signal block diagram. So now what is the complexity in this is it is a mixed domain. As you can see, it is a mixed domain. What is mixed domain? It has both S as well as Z domain, and we cannot use this to design anything because it is in two domains. So there are two ways. Either you can convert everything into fully S domain. So either you can do it in S domain, you have to convert the Z domain things into S domain, or you can convert S domain things into Z domain. So in that case, this will be like continuous time, and this will be like discrete time. So now the question is which one to follow. Either you can do this or you can also do this. So which one is more accurate? Which one is good for controller designing? that we'll be discussing. But just to start with, so the same block diagram, first we'll discuss how to convert into S domain, and then we'll discuss how to convert everything into Z domain. So now this is the approximate continuous time. So how are we approximating? So if you see here, GC of Z, we are converting into GC of S. So from Z domain, we are converting this to S domain. And zero order hold, we are not considering zero order hold transfer function, but instead we are considering delay. So this tau d will have two terms. One is the sampling delay, and the other one is the DPWM delay, which is the on time. So this is sampling delay, and this is the DPWM delay. So the entire total delay we have considered as e to the power s tau d. So whatever delay that is available in the loop, we have merged it into the single block. So single block for delay. So this is a single block for delay. So entire delay we have clubbed into a single block, and everything is in S domain. So what we have actually did is we have taken a continuous time small signal assessment small signal model, which is exactly similar to what we would be doing in analog control. But since this is digital, additionally we are considering delay. So continuous small signal model with delay. And is it accurate? No, it is not accurate. Not accurate. It will. It is kind of an approximation. So we are approximating some blocks by means of delay. So we are taking continuous time, but adding only the delay. So that's why this is approximate model, not accurate. This is approximate continuous time model. But if it is approximate, why are we considering this model? That I will let you know in the final part of this before problem solving. So where we discuss about the model accuracy. So how accurate? It is approximate, but how accurate is this? Can we use this? Until what point we can use this? So all these things we'll be discussing in the future. Until now, approximate continuous time model is the same continuous time model with this additional delay block, that is e to the power minus s tau d, where we consider all the delays in TD. So this is where we are doing everything in S domain. So this is in S domain. So one way is either you can use this model to design the controller or for whatever purpose you want, and but you have to remember that this is an approximate model but not accurate. So there is some accuracy issue, but how close it can match with the accurate model, that we'll see in the upcoming slides. So this is the S domain, and okay, let me erase this part. So if it is continuous time with some delay, what happens now? K loop digital of S. Now say this is K loop digital. K loop digital. It will be exactly same as analog, except this additional term is there. So K loop delay, K loop of S, the new digital in digital control, will be K loop of analog, whatever you are considering in analog, with this additional delay. So we have a question, sir, why small signal model controller design is valid for FSW by 10. So one thing, as we are discussing, the accuracy issue. So when we are saying small signal model, we are approximating what? Ripple. We are neglecting ripple. Ripple information is missing, right? So it is not the actual signal. Ripple information is missing. So that's why in the previous course, SAR was matching the small signal model versus actual switch simulation. So because we are ignoring some information, it itself says that the model is not accurate. So, but the question is until what point is it accurate? So for that purpose, in the previous course, SAR has showed these two. So SAR has done the switch simulation. Say the inductor current is like this, and like this. Say something like that I have drawn. Now SAR will consider the small signal transfer function, and SAR will see how close is it matching. So SAR will get say something like this. Now what SAR has done, SAR has increased the bandwidth of the controller and see whether it is still matching or not. So after some point of time, whatever small signal transfer function that we get, it will not match and it will deviate from the after certain bandwidth. Say in this case FSW by 10, model will deviate. So Sir has considered this and shown that until what bandwidth does it match. So this small signal has some accuracy issues. So Sir has seen what is the bandwidth until which we can consider this small signal. So the model itself is not valid after FSW by 10. That's why when we consider small signal model, we cannot go beyond FSW by 10. That's why this issue is there, because the model itself is not valid. But this is in the case of voltage mode control. Also Sir has shown in current mode control, we can increase the bandwidth to FSW by 10 or FSW by 5, I guess. So we can still push the bandwidth until this point. So everything comes from the model accuracy. So you have to see whether the model is accurately matching or not. So Sir has seen that or shown that current mode control small signal model is quite accurately matching with the switch simulation until this frequency. So we can consider that small signal model until this point, and hence we can design the controller. So it is coming from the model accuracy issue. But when you go for large signal, there is no approximation. You are considering the actual large signal. So large signal is accurate, fully accurate. There is no approximation. So that's why we can go bandwidth beyond FSW by 10. This Sir will show when he discusses about large signal. I hope this has cleared your query. So again, the tau d, as we have discussed, one is the sampling delay or the ADC delay, and the other one is the DPWM delay. So tau d is the total delay that is there in the loop. So in the S domain, we are considering whatever is there in the continuous domain with extra delay. So now if we club these two, then what happens? We will get GVD into e to the power minus s tau d, right? So this is the GVD with delay. So that is what we have written here. So the GVD of s with delay is GVD of s into e to the power minus s tau d. So we are additionally getting this delay in S domain. So this is all about S domain when you convert everything into S domain. And as we have discussed, it has some accuracy issues, which will be further investigating in the upcoming slides. And it is also available in this paper. So not paper, this is a book. So you can go through this book if you want further information regarding this. The alternative approach is converting into Z domain. So say we have zero order hold block, right? Zero order hold. So what is the transfer function of zero order hold? We know that zero order hold transfer function is, say, G zero order hold of S is 1 minus e to the power minus st by s. This Sir has discussed in the lecture, and it is simple. So you give we give one delta of t, and zero order hold will hold for some time. So from this you will get the output transfer function and then input transfer function. So we divide this by this to get Z0H, and it is very simple. That's why I'm not going in detail. So zero order hold transfer function is 1 minus e to the power st by s. So we know this transfer function, and say this is some g of s. Some another block is there with transfer function g of s. Now what is total g z of s? G z of s is simply g of s into g zero order hold of s, right? So 1 minus e to the power minus st by s into g of s. That's what Sir is writing here. So Sir has brought this 1 minus e to the power st outside and s inside. So why we have done this? We have done this because this is in S domain. If I want to convert it into Z domain, what we usually do, we convert it into time domain, and then you have to convert it into Z domain, discrete domain. But we know that Z is nothing but e to the power minus st. So e to the power minus st we can directly replace by Z inverse, and this is Z transform of g of s by s. So now this is in S domain. We have to convert it into Z domain. So if there is a block attached with zero order hold, and if the block transfer function is g of s in S domain, then gza, the combined transfer function in Z domain, is nothing but 1 minus Z inverse into g of s by s. Now coming to our, so this is the same thing that we have written here. So this is the G of S. So now what is G of S here? So G of S is this entire thing. So sorry. If you see the G of S, let me change the color. Maybe I'll make it violet color. So G of S is this entire thing. So this is ZOH and this is G of S. Now what will be GZ of Z? So this is GZ of Z. So G of S is this G of S, which is GPWM of S into GVD of S into e to the power minus S tau d. Also the gain will be coming. So if we assume there is no gain, then it is 1. So this tau d is the total delay. And G of S, this is the modulator gain. And this is the control to output voltage transfer function. So this gives us G of S. Now we have to do G of S by S, and then we have to convert it into Z domain. And after converting into Z domain, we have to multiply by 1 minus Z inverse. Then what happens? We'll get, we'll have a loop with, so now K loop of Z will be what? K loop of Z will be GC of Z into GZA of Z. So now everything is in Z domain. Now we will, if you want to check the stability or anything, then you can do everything in Z domain. You can use this model also to design controller. But the issue with the Z domain is we are not that much habituated to Z domain, because in Z domain the stability happens like the system is said to be stable when it is inside the unit circle, right? And it is difficult to visualize. If I give you a transfer function, it would be difficult to visualize whether it is lying inside the unit circle. But whereas in the case of S domain, it should lie here. It should lie within the unit circle, and here it should lie on the LH. So this is the S domain. So we are more habituated to S domain because we can easily visualize things, and we can see whether the system is stable or not. It would be much easy for us. So that's why we prefer S domain and not Z domain. So but there is a model accuracy in S domain. So how accurate is this? That we'll be discussing. So these are the two approaches with which you can finalize the small signal block diagram. So this is all about small signal block diagram. If you have any questions at this point, we can stop and discuss, have a discussion. Else we can move into current loop stability. Yeah. Yes.
That Z is equal to e power st, right?
Sorry. E to the power st. So sorry, Z is equals to e to the power st, and e to the power minus st is equals to Z inverse. Yeah. Thanks for correcting. Yeah. Okay, if you do not have any further queries, we can move on to the next one. So now we have discussed about the small signal block diagram. Coming to current loop stability. So Sar has discussed current loop stability of two current mode control architectures. One is mixed signal and the fully digital. So in the case of digital, say, or I should not say digital or mixed, say mixed signal or fully digital, is there any constraint for stability? So any constraint for stability? So what are the conditions that we have to satisfy in order to keep the system stable? So what are the conditions that we are going to discuss? So coming to the first one, which is fixed frequency. As you people know, in fixed frequency, mixed signal peak current mode control. So as the frequency is fixed, so the time period is fixed, and this is the duty ratio. So the time is D into T, and this is the off time, this is the on time. So this is T on and this is T off. And this is IL of n, and this is IL of n plus 1. So this in the n cycle, this is the n point ILN, this is the n plus 1 point IL n plus 1, and this is I reference of n. So now if I want to write IL of n plus 1 in terms of ILN, how can I do? I know this M1, right? So I can, knowing this point, I can write this point. So what is this point? I can write this point as ILN of n plus M1 into dt. So the slope into the time period gives me this vertical value. So this plus that vertical value gives me this peak. So this peak point is IL of n plus m1 into dt. Now from here, if I want to go to here, what can I do? So now this IL of n plus 1 is nothing but IL of n plus m1 into dt minus m2 into t minus dt. So whatever I am getting IL of n plus 1 in terms of ILN. So from here I went to here. So which is IL of n plus m1 into dt. And again from this point to this point, it is minus m2 into t minus dt. So that is what we have written. So IL of n plus 1 is IL of n plus m1 into t and t, which gives me the peak value. And from the peak value, again, I have to subtract this m2 into t minus d of t or 1 minus d into t to get this IL of n plus 1. Now, what is the duty ratio here? Duty ratio, how to define duty ratio? Duty ratio is nothing but this peak minus this point by the slope, right? So d of n of t is nothing but this is the peak value, this is the value, value. So peak minus value by the slope gives me this duty ratio. Now, if I substitute this back in this equation, what will I get? I will get term in terms of IL of n plus 1. Then I am doing perturbation. So I have substituted this. So first what I have done, I have substituted and then perturb the variables. So all constant terms will be vanished and we are left with IL perturb of n plus 1 is equals to minus m2 by m1 IL perturb of n plus 1 plus m2 by m1 into I reference perturb. So there is less than a minute. So if this meeting ends, I'll rejoin the meeting. Kindly rejoin the meeting so we can continue the discussion. So until this point, like, have you understood the concept? How we are getting this expression? Hello.
Yes.
Okay. So after getting
sir,
this
but,
point, okay. So after getting this point, what will I do? I'll apply Z transform. So we have to apply the Z transform. So if I apply Z transform, what shall I get? I'll get IL perturb of Z into Z. So this is n plus 1, right? So this is Z into IL perturb of Z is equals to minus m2 by m1 into IL perturb of Z plus 1 plus m2 by m1 into I reference perturb of Z, right? So I have applied the Z transform and I have written the final expression. So if I from this expression, if I calculate from this expression, if I calculate I reference or IL perturb of Z by, you can see, right? Hello.
No, sir.
You cannot see my
The
screen.
screen is not. Now this is.
Okay. So 1 plus m2 by m1 by Z plus m2 by m1. So this is the inner current loop small signal transfer function. We know that any transfer function will be stable. If it is in the S domain, the pole should be lie on the LHP side of the plane. And in the case of Z domain, it should lie in the unit circle. So from this, what we'll get, Z is equals to, maybe I'll use a dark color. So we'll get Z is equals to minus m2 by m1. And we know mod Z is less than 1. So mod Z means mod m2 by m1 less than 1. So this is the condition. But in the case of buck converter, what is m2? M2 is V0 by L. And what is m1? M1 is V in minus V0 by L. So if I apply, what shall I get? I'll get actually V0 by L. So V0 by L is on the LHS side and V in minus V0 is on the RHS side. So I will get 2 V0 is less than V in. V0 is what? 2 into D into V in is less than V in. From this, what shall I get? What is the inequality that I will get? V in get cancelled and D is less than half. So D is less than 0.5. So for the current loop to be stable, I have to ensure the duty ratio is less than 0.5. So this is the duty ratio. So this is the bottleneck in the peak current mode control. So for peak current mode control, in order to maintain the system stable, duty ratio should be less than 0.5. And similarly, for valley current mode control, duty ratio should be greater than 0.5, else the system will be stable. But if you want to operate more than 0.5, you need something called ramp compensation in order to keep the system stable. So these are the basic aspects that we need to keep in mind when we are going for peak current mode control. So if the duty ratio is say less than 0.5, then we can go for peak current mode control. If the duty ratio is greater than 0.5, then we have to go to valley current mode control. Peak current mode control, I can still operate more than D greater than 0.5, but I need ramp compensation to keep the system stable. So this is all about mixed signal, fixed frequency peak current mode control. So if you have any doubts, you can ask us. We can go into the full digital.
Hi, what happen if digital loop is closed?
So this is all about inner loop, inner current loop stability. When you close the outer loop also, still this will hold, but in the case of fully digital, it will not be the same. So in the case of mixed signal, when you close the outer loop as well, this should be fine, duty ratio less than 0.5, but there might be very slight, it might not be exactly 0.5, but still we can operate it close to 0.5. But if you see the system is slightly unstable, then you need to add small ramp compensation to make it stable. Whereas in the case of fully digital, it will change drastically. So whatever we are considering, it is all current loop stability. So we are considering the inner current loop stability, not the overall system stability. Or overall system stability, we need to consider the K loop. And then we have to consider the loop transfer function, and we have to ensure all the poles are less than 1, or all the eigenvalues are less than 1. And accordingly, we will get the gain values, controller values. Is that clear?
Yes.
Hello.
Yes.
Okay. So now we'll move into fully digital peak current mode control. As you know, in fully digital, we are using something called ripple emulator. So we are taking IL, taking a sample with 1 cycle delay. And so if you see the sample that of the IL, I am using, or I am taking the sample that in the previous cycle is used in the present cycle, and using from that point, the inductor or the emulator has started. So similarly, whatever value that we got in the previous cycle, from that point, we are emulating the ramp, and whenever it hits, see, this is IL. So IL is not hitting the peak. IE, which is the emulated ramp is hitting the peak, I reference of N. So whenever it hits, then the duty ratio will be turned off. So until this point, so here we are doing the peak current mode control of the emulated ramp, not the actual. That's why it is called fully digital. And this is what uniform sampling. We are taking uniform sampling with 1 cycle delay. Let's say this is fixed frequency, so we are considering uniform sampling, and with 1 cycle delay, because we have to emulate the inductor current. So the ADC has to process it, right? So ADC will have some sampling delay, and that's why we are emulating it in the next cycle, not in the present cycle. So because of this 1 cycle delay, there will be some stability issues, and we have to consider that while implementing this in the hardware or simulation. So like last week, I didn't get time to show the fully digital current mode control. Do you want me to show it quickly, or have you understood? If you have understood, we can skip this part, but if you have some confusion, maybe I can quickly summarize it. Do you want me to skip, or if you have gone through and I have understood, then we can skip? Hello. The MATLAB simulation, if you want me to skip, then I can skip. If you want, if any one of you want, then I can still show, but fine. If you stay calm, then I do not understand. If you want me to show, I will show. But if you do not want, then does anyone want me to show MATLAB simulation?
Can see, sir. Yes, fastly.
Okay. So let me go to the MATLAB. Let me quickly week 3 in MATLAB files. It is in which lecture? 27. So buck converter. So all the controller like the codes are same, except we are using MC instead of normal slope, and MC is considering 2 times V in by L. That thing will come in the next slide. But all the code lines, everything is same, only except this simulation part. So I am opening the Simulink. So in the Simulink, as we have discussed, everything will be same. Okay, in the meantime, let me simulate it so that we'll get these values. So everything remains same except this digital controller part. So if we go inside the digital controller part, so we got the results. But before going into the result, let me quickly show this. So maybe I can use some annotation here. Let me keep this on the top part. Okay, so if you see this part, this is exactly same. So this is same as peak current mode control, right? So we are taking V0 and we are using uniform sampling. So this is the switching frequency that we are using for uniform sampling. And after this, we are putting a memory block. So this is the memory block as we have discussed. Now this is giving V sampled voltage, which is subtracted from reference, which is giving us V error voltage. Now this is a digital PI controller. So let me go inside. So if I go inside, it is exactly same as what we have already discussed before. So this is KP into V error. So this is the output of KP. So this is proportional controller output, and this is the integral controller output. And what is UI? We have discussed UI is nothing but KI into V error plus UI of n minus 1. So this is UI of n. Sorry. So this is UI of n, right? So this is UI of n, and we are giving it to this block, which gives us UI of n minus 1. So UI of n minus 1 plus Ki gives me UI, which has to be added here. So this is exactly same as the previous thing, controller, what we have discussed. Now if I go to again the outside block, let me delete this. So if you see now this is I reference, right? Output of the controller is being compared with the emulated. So forget about this part currently. I will go inside. If you come this, so IE is compared with the I reference, which is giving me reset pulse, and set pulse is coming from this switching frequency. And I have mentioned due to the data conversion, this data and this data are not compatible. So we are using some data conversion block to convert it from double to Boolean. And then it is giving me the gate pulse. So everything is exactly same except this emulated RAM, right? So now if I go into the emulated RAM, so emulated RAM has 2 parts. So first, let me discuss the left-hand part. So first, let us discuss about this left-hand part. So this is IL, right? So we are taking uniform sampling. So IL, say it is like this, IL. So we are taking what? Uniform sampling. So say maybe we are taking with some delay. So here I am taking, and here I am taking, and here I am taking. So this is what IL of n, and IL of n plus 1, and IL of n plus 2. So this is giving me that red color, whatever red color dots I have shown, this is giving me that. But I want one cycle delay, right? As we have discussed, we want to insert a one cycle delay. But how will I insert one cycle delay? I have to use a block that gives me here, right? So now I want IL of n here. So whatever sample that I have taken, I want it to be given here, and IL of n, I want it to be here. So IL of n plus 1. So I am using one additional block, which will act like a delay. So this is that whatever pink color I'm showing. So first I'm sampling it and then I'm delaying it. So this is the sampling part and this is the delay part. Right. So this gives me one cycle delay inductor current sample. Now, how I am generating the emulator? So emulator should start from what point? It should start from IL of n minus 1, right? So one cycle delayed inductor sample has to be added with the emulated RAM. So that is what we are adding. So from what point it starts? It starts from the IL previous sample that has been taken. So on top of that, we want to add an emulated RAM. So how are we generating emulated RAM? So for emulated RAM, it has to continuously increase. So what we are doing, we are taking an integrator and we are continuously integrating it the value. But if you actually take an integrator and integrate it, the slope will be what? 1. But how much slope we need? We need MC. So that's why I'm multiplying MC with the gate pulse. And if I quickly come back here to my screen, okay, first let me delete all the drawings. So MC should be emulated until it hits, and after that it should become 0, right? So I am multiplying the MC with the gate pulse. Say the gate pulse is like this. So whenever gate pulse is 1, this is 1. Whenever this is 0, this is 0. So the emulated ramp will work whenever the gate pulse is 1. So whenever the gate pulse is 1, it will be emulating with the slope of MC. After that, this will become 0. So 0 plus IL of n will be what? IL of n. So it starts from IL of n, n minus 1 value. And on top of that, it is being emulated. And then after that, it is being what? It is staying at that particular value itself. So if I go into this, you can see this block, there is nothing but integrator with a reset. So it is continuously integrating. So integrator means it will keep on adding, right? So it will keep on adding, and I have given the falling edge as reset. So whenever this gate pulse is turned off, I am detecting this falling edge and I am using it as a reset. So this is the emulated current, and it is being compared with the reference current. So just only one additional block is needed in the case of emulated RAM or fully digital current mode control. Apart from that, everything is same as current mode control. Now I have got one result, but let me also simulate it again to show the emulated RAM. So in the buck simulation, I need emulated ramp as well. So I will show both inductor current as well as emulated ramp so that you can have a better understanding. So this is V0 and this is the inductor current. So let me pull this down. You are listening, right? All of you?
Yes, sir.
Yes,
Okay.
yes.
So if I zoom in this part, okay, but let me change the emulated ramp color. So both are red. Maybe I'll make inductor current blue and emulated ramp red. We can directly simulate this. Sorry. So now my inductor current is in blue color and emulated ramp is in red color. So if you see, this is my inductor current and this is my emulated ramp. So emulated ramp is hitting the reference. Maybe I can use annotation and quickly show. So this is my emulated RAM. This is my inductor current. This is my I reference. So as you can see, if you draw a straight line, so whenever the emulated ramp is hitting the I reference, at that time inductor current is turned off. So if we go and see the actual transient response, then it will be much clear for you. Maybe I will take this part. So if I use again the annotation and I can show you. So let me use a different color. So let me use pink color only. This is IL sample, right? If you take this IL sample, if you see the emulated ramp is started from here, and whenever it hits, it got reset and it is staying at the same value. And again, this new emulated inductor current sample is being taken, and from that point it is being emulated, and then it is staying at the same value. So you can see this 1 cycle delay, right? Everywhere it is happening. So, and on top of that, it is being emulated, and whenever it hits, we are using that falling edge to reset the emulator, and it is staying at the constant value. So only some slight modifications, and it is a bit complex. So this is it. And the voltage, if you let us see where we are sampling. We are sampling right at the FSW point, so it is being updated accordingly. So it is quite similar to current mode control, peak current mode control, except that there is slightly some complexity. And we have discussed about the emulator. What is the emulator? How emulator works. Now coming to the our current loop stability, we are discussing about current loop stability. So it is the same expression as current mode control, right? From IL of n, I am getting the peak value, which is IL of n plus M1 d and t. And then from there, I am subtracting minus M2 into 1 minus d of n into t. But the main difference comes in the duty ratio. In the case of current mode control or mixed signal current mode control, we are comparing IL comma I reference, right? So the duty ratio term is dependent on IL and I reference. But in the, so if I go back quickly, so it is I reference minus IL of n by M1, slope of inductor current. But in the case of fully digital, I am taking 1 cycle delayed sample with the emulated ramp. So this is because there is a 1 cycle delay. And this is because we are using emulated ramp instead of inductor current. So this is the expression for duty ratio, because if you see, this is I reference of n, right? So this is I reference of n, and this is the duty ratio we are getting from the emulated ramp. So this is the value point, which is what IL of n minus 1. So if you consider the slope is nothing but MC is equals to peak point, which is I reference of n, minus value point, which is IL of n, by the slope. MC is nothing but the duty ratio. So this is the only difference between the fully digital current mode control as well as mixed signal current mode control. Now, if you substitute back this and perturb, so again we are doing what? Substituting d of n in that, and then we are perturbing it. Right, then I will get this expression. So MC is the new term, right? So and IL of n minus 1 is again a new term that is coming. So because of this 1 cycle delay, there will be some constraints on or stability issues with the fully digital compared to mixed signal. So let me take this value as A. And if I apply Z transform, I will get what? Z into IL perturb of Z is equals to IL perturb of Z plus A into I reference perturb of Z minus Z inverse. So if I do IL perturb of Z by I reference perturb of Z, I will get what? A by Z minus AZ inverse plus 1, which is if I multiply by Z, I'll get ZA by Z square minus A plus 1, AZ plus 1. Or I think I made a mistake. So until this point, it is fine. So after this point, we'll get, if we multiply by Z, we'll get AZ by Z square plus Z minus A. Understood how we are getting this expression? I have applied Z transform, and then from there I am getting this, where A is M1 plus M2 by MC. MC is nothing but the emulated ramp. Have you understood? Hello.
Yes, yes.
Okay. So again, the poles should be lying inside the unit circle. So if you calculate minus b plus or minus square root of b square minus 4ac by 2a, and then you apply, you will get this expression. So what is MC? MC is nothing but M1 plus M2. I know M1 is V in minus V0 by L, and M2 is what? V0 by L. So if I add, I'll get what? V in by L. So MC condition is V in by L. But this is for current loop stability. But if you go for closed loop, complete closed loop, the MC requirement increases, because in closed loop, if you use this MC, system will be unstable. So this is one what that sir has published in one research paper. So if you want further details, it is also mentioned here. So if I go back to the Simulink, that's why sir has considered here what 2 into V in by L, right? It is, but the current loop stability says greater than M1 plus M2. I'll also show you if it is 1.1, then what will happen. So let us simulate. So for current loop stability, only current loop, then this is fine. But when we consider the overall closed loop, this itself is not sufficient. We want higher emulated RAM than this, because of which the requirement increases. So this is the inductor current. As you can already see, this is not stable. This is not a stable. So maybe there is multiple emulated RAM as well as inductor current. So what we can do is we can hide the reference as well as we can hide the emulated RAM as well. And then we close this and we'll plot it again. So we can directly see the inductor current and output voltage. So this is the output voltage, and if you see the zoomed in portion, it is not stable, right? So it is having some subharmonic instabilities. So it is not stable. So you can see it is not stable. So this kind of subharmonic instabilities will be occurring if you do not provide the enough MC. So that is why, and the voltage is also like not repeating after one cycle. It is repeating after few number of cycles. So this is what we call subharmonic instability, because of which 1.1 is not sufficient. Some high value is needed. And if I simulate it, now it becomes stable, because the emulated RAM requirement we have increased. We have given more emulated RAM. So now, as you can see, it is stable. The inductor current is not repeating. It is just repeating after one cycle, no subharmonics. So these are a bit high level. So we will be not be implementing this in the hardware. So this is somewhat high level. So just you have to know the concept as well as the stability issues as well as the RAM requirement. So MC is greater than M1 plus M2 for current loop itself, not for the entire closed loop. So if you have any doubts until this point, we can discuss. If no, then we can move further. Till this point, it is clear, right?
Yes.
Okay, so there is something called large signal discrete time modeling, where we consider the large signal and we do something called discrete time. So DT means discrete time, CT means continuous time. So we do discrete time modeling. So first we'll discuss about the analysis, and then I'll show simulation if you want, and then I can again validate it. So this is the thing that you have to start with. So this is the state space solution. From the state space solution, so you know x dot is equals to ax plus bu. Then what is the solution? This will be the solution. Say aq bq. We know this is the solution. This is very standard. So you just have to. This is a first order differential equation. So you can multiply by e to the power at, and you can directly get the expression. Now here u of t is what u of t is time varying, but in our case, when we consider a buck converter, ax is equals to bx plus ax plus bb, right? Usually we assume it to be almost constant. It is time varying, but majority of the time it is constant. It is not continuously varying. It is, there is slight variation, but it is majority of the time constant. So in that case, you can take this u outside. Now it is e to the power a into t minus tau b into d tau. Now you can integrate this, and you can apply the integral this definite from t naught to t, and then after doing this you will get this expression. So this is very simple mathematical expression that you can try. So after doing this you will get this expression. So this is what we consider. So from the actual equation we are getting this solution. So x of t is nothing but e to the power a into t minus t naught x of t naught. So if I am moving from say time period t naught to t, and if I know x of t naught, and if I know what are the matrices A, B, I can get x of t by this solution, right? That's what this equation says. So now what I'm doing, okay, let me change the color. I will go to somewhat dark color. So this is my sample from here. So from this point to, I'm going to this point. Say this is my nt, I'm going to n plus 1t. So how many regions are there? So let me come back to inductor current. So from here to here one region, and from here to here another region, and from here to here another region. Say this is my xn, this is my xn plus 1, right? So I need to get xn from xn to xn plus 1, I need to get in relation. So my aim is I need to get xn plus 1 in terms of xn. So this is one region, M2 region, which is the off region, and this is the M1 region, on region, and again this is M2 region, off region. So I know that in the case of on region, the matrices are A comma B, right? And during the off region, in the case of buck converter, they are A comma 0. So in the case of off period, I know B matrix is 0. Do you agree or not? In the case of buck converter, we are discussing about buck converter. Hello? Hello?
Yes, sir. Those
Yeah.
input is 0.
Yes, yes. So it is disconnected from the input. So B matrix is 0. So in the case of mode M2, say this is my x1 point, this is my x2 point. So let me clear this. So in the mode M2, I am going from x1 to x2, right? So I am if I put B matrix 0, what will I get? I will get x of t is e to the power a into t minus t naught into x of t naught, right? Here my x of t is x1, and t minus t naught is the time difference. Time difference is what? This is the sampling delay from this point to this point. So x1 is nothing but e to the power ats into x of t naught is what? Xn. So that's how I am getting x1 in terms of xn. So we have a question here. Voice is not audible. Is my voice not audible? Can anyone please confirm? Hello, I'm audible, right?
Nice.
Okay, Anis, maybe you can try rejoining it, and let us see if we can hear my voice. So this is mode M2. Okay, maybe I'm not audible to him or let me mention. Others can hear. Okay, so that's how I'm getting x1 in terms of xn. Now this is x2. I want x2 in terms of x1. Now what are the matrices A comma B, right? So A comma B are the matrices, and I have to substitute again here. So here now what is my x of t? X of t is x2. Maybe I'll. So my x of t is what? Now x2. And my x of t naught is what? X1. And what is the time period? Time period is my on time, right? So this is my on time, t on. So e to the power a t on, and e to the power a into t minus t naught, again e to the power a t on minus I into a inverse into b in. So right from this equation, I am getting x2 in terms of x1. Now my final region is again M2. M2 means B matrix is 0. So only first part will be there. So this part will be there. And my matrix is A. And what is my time period from here to here? It is nothing but total time period minus T on, which gives me off time. So off time minus sampling delay. So this is T minus T on minus TS. So this is T minus T on minus TS. So this is T minus T on minus TS, and this part is TS, and this part is T on. So the total is T and this is T on, this is TS. So this is T minus T on minus TS. So it will be exactly same like this, except the time will change. Now my xn plus 1 is e to the power a into T minus T on minus TS into x2. So I have got xn plus 1 in terms of x2, x2 in terms of x1, and x1 in terms of xn. So now what am I going to do? I am going to do this. I am going to substitute this x1 in this expression. Now I will get x2 in terms of x1, and then after that I will substitute x2 in terms of xn. Then what will I get? I will get x1 plus in some function of xn. I am not showing the detailed calculation. You just have to substitute. Then I will get my large signal DT model. This is large signal because we are not approximating anything. We are considering all the ripple, everything. We are basically using the solution of the differential equation to get this expression. So I have xn plus 1 is equal to e to the power at into xn, e to the power a into this expression into final expression mean. So this is my large signal DT model. So now we have to, we can validate it. So I got some mathematical expression. I want to validate it. So large signal DT modeling, what we are taking, we have one sample. From that sample, I am getting the sample in the next cycle. Using that sample, I am getting the next sample in the next cycle. So in this way, I am getting the samples. So I can validate it. So how can I validate it? So Sir has shown in his lecture. I will just quickly show. So we are in the...
Hello.
Yes, yes.
Yeah, this is for only fixed frequency modulation.
Yes.
Can we apply this for variable frequency modulation
Frequency as
also?
well.
Okay.
There is one SAR's paper. I think SAR has mentioned in this lecture. I have not copied it here. So in that SAR
Okay.
has, I think, some analytical discrete time modeling paper is there. So there
Okay.
SAR has generalized for fixed frequency as well as variable frequency.
Yeah, okay.
And using
Actually,
that,
it will be helpful. Actually, it will be helpful if you put a paper link in the chat box so that.
okay. Maybe I'll update it here. I think I have not updated here. Or
Okay,
maybe I will add it in the YouTube video description.
Okay.
Or maybe I'll add it here after this video has ended. I'll put and I'll update in the Google Drive.
Okay.
Okay, so there are two things. First thing is the actual simulation. So this is our mathematical model and we want to validate it. So with what we'll be validating, we'll be considering a switch simulation. So SAR has considered the exact switch simulation of digital voltage mode control. Everything is same. So let me run this. So let me go back to the code part. And where is the code part? This is the code part. So I am running it. So now it will give me the actual switch simulation, which we have been doing since last week. Now then, so this is the actual switch simulation with the V reference. So let me remove the V reference also, plot buck simulation, or okay, let it be. So there is no issue. Now after that, we are comparing it with discrete time large signal model and trailing edge. So this is trailing edge as this is like we are considering normal trailing edge voltage mode control. And in the case of large signal model, so SAR has first considered buck parameter and then DT model matrices. What is inside DT model matrices? We have A on, A off, and B as well as C matrix. So A off is A on, right? So in the case of buck converter, both A1 and A2 matrices are same. And whatever A matrices that we have derived previously, that SAR has just mentioning it here so that we can directly use them. And after that, the main very important thing that one thing that you should be concerned is the initial condition. So whatever initial condition is very crucial. So initial condition for switch simulation as well as the discrete time, the code we have considered, both should be same because we are matching, right? So when we are actually trying to match something, both simulation and code should start from the same point. Else it will not match in the beginning. After that it will match. But if you want it to be matched from the very beginning of the code, initial conditions should be same. If it is not same, then after some point they'll match. But at the initial condition, they might not match because the points at which the converter is trying to start are different. So that is the one important point that you should keep in mind. So after that, SAR has considered this and SAR has then gone into the DT dynamics. So what is DT dynamics? I'm going into DT dynamics. So SAR has considered from n equal to n transient minus 1. So until n transient, first SAR will be considering buck DT dynamics, then SAR will give a transient. So everything has to match with the switch simulation. So from whatever current to whatever current you are going, whatever resistors you are using in the switch simulation, same resistors SAR is using here, and at what point SAR is giving the transient in the switch simulation, same SAR has considered in the code. So they will be exactly timely matched, and it will be exactly matching. So after that, what DT dynamics, right? So buck DT dynamics is just the same thing. So here we got this expression, right? E to the power 80 into xn. So one important point, e to the power 80 is exponential to a matrix, right? It is not e to the power a. E to the power a is just a constant. E to the power 80 is exponential to a matrix. So normal exponential is exp. Matrix exponential is expm. Again, just a heads up, there is less than a minute. So if this meeting ends, kindly rejoin in the same link. So that's why SAR is using expm, because it is a matrix of A. So expm is exponential matrix, M for matrix. Exp is normal exponential of a constant. So SAR has mentioned all the matrix, e to the power A on T, and the other matrices. And I'm not going in details, so it might look scary, but this is just the mathematical implementation of this equation. So after that, we are plotting the sample point. So let me simulate it and check whether they are matching or not. If the meeting ends, kindly join it so we can continue our discussion. So the red circles are the sample points. So as you can see now, there you can hear me, right?
Yes, sir.
Okay. So as you can see, they are perfectly matching. And let me go to the transient part. So this is the transient part. So we are taking the TS sample, right? So as you can see, they are perfectly matching in the transient. And so whatever model that we have derived, mathematical model, it is perfectly model, and it is a large signal model. So we can rely on this model. And it is perfectly matching with the inductor current. Now, if we move on to the voltage, let us see the voltage during the transient. So the sample is being updated, and this is also voltage sample. So if you zoom in, so wherever the reference is being updated, the sample at which switch simulation is taking, that is exactly matching with whatever we are getting. So the green color circle is the large signal model, and this is the sample voltage in the switch simulation. So they are perfectly matching. So this is just to show that whatever model that we have considered, it is perfectly matching. So this, we can rely on this model that it is perfectly matching. So this is the large signal DT modeling. So from large signal DT model, we'll get something called small signal DT model. Why we do small signal DT modeling? Because to design the controller. So whatever controller we'll be designing using small signal. So from the large signal, we'll perturb it across or around the steady state, and we'll get small signal DT model. So there are two approaches, approach 1 and approach 2. In approach 1, there is something called phi comma gamma method, and in approach 2, it is something called Jacobian method. So approach 1, first we'll discuss, and approach 2, then we can go into approach 2. So approach 1, there is phi and gamma, as I have mentioned. So phi is mainly due to the initial state perturbation, and gamma is due to the duty ratio perturbation. So first we'll discuss about phi. So if you discuss about phi, this is the large signal DT model that we have obtained in the previous slide. So this is the large signal DT model. Now, this is the xn, right? So duty ratio, I'm keeping it exactly same. I am perturbing the xn from this point to this point. So then there will be a perturbation here. So we want to see xn I have perturbed by xn perturb. So after one cycle, what is the perturbation? So here the perturbation is phi into xn perturb. So I want to see if I have given a perturbation of xn plus 1 in this present cycle. It will be say product of phi into xn perturb. So what is phi? I want to see. So how we have derived the DT model, exactly we can do. So there are again 3 regions. So this is say region 1, this is say region 2, This is say region 3. Now we have considered only xn perturb. So xn perturb. So initial state perturbation means only xn is perturbed and duty ratio perturb is 0. So T on perturb is 0. Right. So there is no perturbation in T on. So this entire term is constant, right? So this entire term is constant and we are changing only xn. This entire term remains constant. So if you perturb, what you will get? We will get this expression xn plus 1 perturb is equals to e to the power at xn perturb. Right? Because the second term is constant. If you perturb it, it will be 0 because it is constant. So using this, we have to define or derive xn plus 1 perturb. So let me change the color and let me go to say red color. So this is xn perturb, right? So maybe this point at the end point is x1 perturb and this is x2 perturb. So how can I write x1 perturb is nothing but e to the power at, right? So this is in the off period, but in buck converter both are same. A into time period is what? Ts into what? Xn perturb. Now x2 perturb is on time into x1 perturb, right? So e to the power a into t on into x1 perturb. So now I got x2 perturb in terms of x1 perturb. Now then xn plus 1 perturb is what? Xn plus 1 perturb is whatever time that is left, e to the power a minus t on minus ts into x2 perturb. So now if I back substitute just like what I did in the large signal model, so substitute x1 here and substitute x2 here, then we will get this final expression. So if you consider, so this term e to the power a2, or you can say, see, this is off region, right? So off region, SAR is considering a2 to be the matrix, and on region, SAR is considering a1 to be the matrix. So e to the power a2 into ts, so whatever we have got here, into, then this corresponds to this region, which is a1 into t on. So as it is on time, SAR is considering a1, but in buck converter, both are same. So a to the power a1 into t on, right? And then the other third region corresponds to this region, which is a into t or a into t minus t on minus ts. Again, this is off region, so a2 matrix, but in buck converter, both are same. So e to the power a. So t on is dt, right? So by substituting this, we will get this expression. So this is only due to the initial state perturbation. So we have defined what? I have defined xn plus 1 perturb is phi into xn perturb. So what is phi? This term is phi, right? So this entire term is my phi. So that entire expression is phi. So what I did, I have not perturbed duty ratio. I have perturbed just xn, and then I'm checking if this perturbation is xn perturb in the present cycle, what is xn plus 1 perturb in the previous, I mean next cycle, and then I got this expression phi. So in this slide is clear, right? Hello. Hello. Until this point, is this clear? Okay. Then so now we have considered initial state perturbation. So in the next state, first we'll consider duty ratio perturbation, and after that we'll consider both the perturbations. So if we consider duty ratio perturbation, so actually this is both the duty ratio as well as the other perturbation, which is the initial state perturbation. So first we have changed the duty ratio, right? So we have changed the duty ratio, and this is the d perturb of n. So d perturb of n, and we are zooming this part. So the duty ratio has changed from this point to this point. So this is d perturb of n into t. Now I want to see if the duty ratio is changed by d perturb of n, what is my xd? So initially duty ratio is until this point. Now duty ratio has increased to this point. So it is turned on for more duration, because of which x2 will be more than x1. First, I want to find what is this xd perturb, and from then xd perturb, I will get this gamma of d perturb of n. And this is phi of xn perturb. So let us not go into this. First, I want to find xd perturb, and then I'll find gamma d perturb of n. So to start with, I know x dot is equals to ax plus b into v in, right? So x dot is what? Dx by dt, right? So if I consider the same thing, I'll get two equations. One is x2 minus xp is equals to a into xp plus b into v into time period, which is d perturb t. Similarly, I'll get for the x1. So one thing you should be clear, this is on time, right? So the matrices are a1, b1, and this is off time. So the matrices are a2 comma b2. So this one is a1, b1. Now the other expression is x1 minus xp is equals to a2 into xp plus b2 into v into d perturb of t. So what I'm doing, I'm considering this expression x dot is dx by dt. So x2 minus x1 by t2 minus t1 is equal to this. So if I send this t2 minus t1 that side, I will get x2 minus x1 for the x2 case. The matrices are a1, b1. a1, b1 into t2 minus t1 is dt, right? The time difference.
Hi, can you
Yes.
explain it 1 second? This
I
part,
want to get this xd perturb. So xd perturb, for xd perturb to know, I need x2 minus x1, right? So I know the expression x dot is equals to ax plus bv, and x dot is what? Delta x by delta t. So if I transfer delta x that side, I will get ax plus bv into delta t. My delta t is what? D perturb t, right? So if I want delta x for x2, it is delta x is nothing but x2 minus xp. So x2 minus xp, and what are the matrices? It is on time, right? So on time matrices are as considering a1 and b1. So a1 into xp plus b1 into v into d perturb t. I'll get one equation. And for the x1, this is the off time. So off time, what are the matrices? A2 comma b2. So a2 into xp plus b2 into v1 into d perturb. So this is the second expression. So I got x2 in terms of xp, x1 in terms of xp. Now subtract 1 minus 2. Subtract 1 minus 2. That will give you this expression. Is that clear? I am getting two equations and then I am subtracting so that I will get xd perturb. You have understood, right? Whoever has asked.
Yes.
Yes. So now I am considering this to be, say, alpha. So alpha into t into d perturb of n. This is the xd perturb. Now from xd perturb, I need to get xn plus 1 perturb. So this is just the same thing. Now it has become what the duty, like the no duty ratio is changed. Just what the previous case, initial state perturbation. So xn plus 1 perturb is e to the power a into time into the previous value. So gamma into dn plus 1 perturb or xn plus 1 perturb. So xn plus 1 perturb will be e to the power a into t into xd perturb, right? And a is what? A2, because this is off time. A is what? A2. And what is this time? Again, this time is t minus t on minus ts. Right. So there is this d perturb also, but d perturb is very less. So that's why we are not considering in this expression. So we got xn plus 1 perturb as e to the power at into xd perturb. So a2, because it is off time, into time is t minus t on minus ts into xd perturb. Now substitute this xd over here. So what we wanted gamma value, right? So again, this entire thing is gamma. So actually this entire thing is gamma. So gamma is e to the power a2 into t minus t on minus ts into alpha into t. Have you understood until this point? How we are getting gamma? Hello? Okay, I have got a question. Yes, sir. Okay. So now I got 5. I got 5. I got gamma. So if I want, now I'm perturbing only either initial state or only duty ratio. If I perturb both of them, then I can apply superposition because it is linear. So in buck converter, I know that A1 is equal to A2 equal to A, and B1 is this, and B2 is 0. So now if I perturb phi and gamma, so this is the small equation, right? Xn plus 1 perturb due to initial state perturbation and due to duty ratio perturbation. And this is both initial state and duty ratio perturbation. So how do I get? So first I'll go to the phi. So whatever phi I got, so phi is this, right? In buck converter, A2 is A1. So e to the power A into t minus dt minus ts into e to the power A into dt into t to the power A into ts, right? So this is my phi. So if I multiply it, I'll get e to the power at. And one thing you have to remember, e to the power A into t1 into e to the power A2 into t2 is equals to e to the power A1 t1 plus A2 t2 only when A1 A2 is equals to A2 A1. Right. This should be clear. So here in our case, both are A matrices. So it is A square equal to A square. So I can add it up. So when I add it up, dt cancel, TS cancel. So my phi is what? My phi is e to the power at. Right. So that is what we are writing. So phi is e to the power at. Now coming to my gamma. So gamma, for gamma, let me use a different color. So gamma has alpha, right? So in alpha, A1 is equal to A2 equal to A, right? So this part will be 0 and my B2 is 0. So my alpha is what? My alpha is nothing but B1, V in, D perturb, T. This is my alpha. And T1 minus TS is what? TD. Total delay, we have considered T ADC plus T DPW. So T1 minus T1 plus TS is TD. So from this I am getting e to the power A2 is nothing but A. So e to the power A into T minus TD. Alpha is B1 V1 D perturb into T. So B1 V1 into T into D perturb. So this is my phi. So this is my phi. And this is my gamma. So this is the small signal that I got from large signal. So to summarize what I have done. So in the first part, this is the approach one. So in the first part, I am doing initial state perturbation. So I'm perturbing only initial state and I have defined this as phi. I obtained phi. In the second part, I have obtained gamma, which is the duty ratio perturbation. And now using superposition theorem, I'm combining both of them for a buck converter. I have got this expression small signal. So this is small signal DT model. So I'm getting small signal. And again, why I'm going small signal to which I'll be using to design the controller in the next week. So I'm getting this small signal. If you are clear with the approach one, then we'll go to approach two. I hope this approach one is clear for everyone. Have you understood till this point?
Yes.
Okay. Yes. So now I'll go to approach two. So even in approach two, I'll be coming with the large signal DT model and I'm considering F. So using Taylor series expansion and using the Jacobian. So from Taylor series expansion, if you neglect the higher terms, I'll get xn1 is a function of both xn. So F is a function of xn comma t on, right? So if I do this perturbation Taylor series expansion, I'll get dou f by dou xn into xn perturb plus dou f by dou t on into tn perturb. And t on is what? dt. So t on perturb is capital T into d perturb. So if I do dou f by dou xn perturb, so say this is first part and this is the second part. This is only dependent on xn and this is only dependent on tn. So if I do dou f by dou xn perturb, dou xn, I'll have to differentiate this because this will be 0. So this is what? E to the power at into xn perturb because I am derivating with respect to x1. So e to the power at is constant into xn perturb. So that is my first term. So my first term is e to the power at into xn perturb. And if I change the color, let me use some different color, say green color for the second term. So for the second term, it is t on dependent. So first term will be 0. So for dou f by dou t on, I need to consider. So let me first multiply this. So I'll get dou by dou t on into, first if I multiply it, I'll get e to the power a of t minus ts minus e to the power t minus t on minus ts into a inverse into b1 into b. So first term is independent of t1, so it will be 0. Minus, we are differentiating e to the power some ax. So it will be e to the power ax T minus T on minus TS into, again, we have to differentiate that A X, right? So differentiation of A minus A T on is minus A. So minus A into whatever that is left. So this minus becomes plus, and A inverse will get cancelled. So the final expression is e to the power A T1 plus TS is by T delay, right? So T minus T delay, B1 into B in into T on perturb is what? T into D perturb. So the T is coming over here. So the T into D perturb. So if I compare this expression with that expression that I got, phi is what? E to the power AT. So this is my phi. And this is my gamma. So is my gamma matching? Let me go and check. E to the power AT minus TD, V1 V in T. E to the power A T minus TD, V1 V into T. So this is approach 2. It might be somewhat simpler because this is more mathematical, and here we have to imagine two kinds of perturbation and then use superposition to implement. So you should be aware of both the methods. But if you want to choose any one method, you can choose this because it is much simpler. You just have to differentiate and get the small signal. So to summarize, xn plus 1 as A equivalent into xn perturb plus B equivalent into D perturb. V naught perturb is C equivalent into xn perturb. My A equivalent, again, this is for buck converter. So A equivalent is e to the power AT, B equivalent is whatever this expression is, and C equivalent will remain unchanged, which is alpha RC alpha. Alpha is, I guess, R by R plus RC. So this completes the small signal DT modeling. So before we go into transfer function, do you have any questions? So our our entire outline is, first we have derived large signal DT model. Using that DT model, we have defined or derived small signal. So this is a large signal DT model, and then we have got small signal DT model by means of two approaches. Now using the small signal DT model, I am getting small signal SS transfer functions. So using this transfer function, I can design controller. So the main aim is to design controller. For that, I need to have some transfer functions, right? So I am going by the actual DT model, discrete time model, because it is more accurate. So that's why everything is in a discrete domain. So this is a discrete domain. If you see, these are everything in e to the power AT. So all these are in discrete domain. So I am going by discrete time for getting an accurate model, because I have told you that continuous time with delay is not that much accurate. So my main aim is controller design. So for controller design, I'm going in this way. So in small signal transfer functions, we'll discuss two transfer functions: control to output, control to current. Control to output is what? Can anyone say GVD or GID? It is GVD, because yes, and this is GID of Z. So I'll derive these two transfer functions from whatever small signal DT model I have derived till now. So so from this small signal DT model, I will derive this small signal transfer functions, which sir will be using in the next week to design the controller design. So this is my large signal DT model, right? So this is my large signal DT model, and this is my small signal DT model. So as I have mentioned, from this, I am getting this. So from this, I have to get this and this. So how am I getting these two? You consider this xn plus 1 perturb and apply Z transform. So we'll get Z xn perturb of Z is A equivalent xn perturb plus B equivalent D perturb. So if I bring this, I'll get ZI minus A equivalent into xn perturb is equals to B equivalent into D perturb, right? So my xn perturb is what? ZI minus A equivalent inverse into B equivalent into D perturb. Do you agree? I am applying Z transform at this point. So I am applying Z transform and I got this expression. So now what is my control to So this is what control to current, right? So this is control to current transfer function. So I know control to current transfer function GID of Z is nothing but IL perturb of Z by D perturb of Z. And I also know that XN perturb has two things. One is IL perturb and the other one is VC perturb. So out for this, I need IL perturb. Say if I multiply by 10 XN perturb. So what will I get? I'll get IL perturb, right? So I will substitute this. So IL perturb is nothing but 10 into XN perturb by D perturb. So from this I can get, right? So I'll get ZID of Z is nothing but 10 matrix into ZI minus A equivalent inverse into B equivalent. Inverse into B equivalent. So that's how I am getting my control to current transfer function. So is this clear? So it is just simple mathematics. I am first applying Z transform. I got one equation. Then according to the definition, ZID is IL perturb by D perturb. IL perturb I know if I multiply XN perturb with 10 row matrix, I will get IL perturb. So I have written 10 into XN perturb by D perturb. From this expression, I get XN perturb by D perturb as this. So which is nothing but this expression. So now I want what GVD, which is what control to output. Control to output. So what is the definition of GVD of Z? So GVD of Z is V0 perturb of Z by D perturb Z. And from the small signal model, I know V0 perturb is C equivalent into XN perturb. So this is C equivalent into XN perturb by D perturb. So if I want to get GVD of Z, it will be C equivalent into ZI minus A equivalent inverse into B equivalent. So this is simple. So from the last signal, I have derived small signal model, and from small signal, I have applied Z transform, and I did some mathematical manipulation to get my two transfer functions, control to current as well as control to output transfer function. These are small signal, and these are in discrete domain. That's why Z domain. Till now, have you understood how we are getting the small signal transfer functions? Hello. Hello. If you have any questions, you may ask. Yes. So this is very simple, just some mathematical manipulation. Yeah.
Hi.
So, yes, yeah.
What this transfer function infers, like GVD of Z? Perturbation due to duty cycle is propagated in voltage or something else?
Yes, yes. So if you see GID, so I is the output here, and D is the input. So D is the input perturbation. So what it means is when we give a perturbation in duty ratio, how much it will change in the inductor current. So I is the output. So by duty ratio is the control variable. So that's why control to current. So I'm giving perturbation in control and how much is the change in the current. These are small signal. So very slight small perturbation around the steady state. If I give what is my current perturbation. Similarly, control duty ratio perturbation I am giving, and I want the voltage perturbation. So that's why control variable duty ratio to output. So how much change in the output I'll observe if I give some perturbation in duty ratio.
Okay. Actually, which transfer function to be used in our controller design?
Yes, yes. So I'll come. So you will be needing this as well as this. So in voltage mode control, you will need only this. In voltage mode control, you will only need this. But in the case of current mode control, you will be needing both. Why? I'll discuss in a few minutes. So in the upcoming slides, I'm about to discuss those. So first we'll go into, so whatever small signal transfer functions we have got from the small signal DT model, which we got from large signal DT model. So using the small signal transfer function, first we'll consider closed loop diagram. So closed loop diagram, and from this, how to get the stability, and as well as the loop transfer function. And why do we get loop transfer function for my controller design, right? So I'll try to achieve some certain bandwidth, some phase margin. So what is my GC? Accordingly, I'll get my GC so that my loop transfer function will have this bandwidth and small signal. So from whatever small signal model, small signal DT model, we are deriving this small signal transfer functions that I'll be using first for digital voltage mode control. Digital. And using this, I'll derive stability as well as loop transfer function. So before we go into the description, so this is my small signal model. So small signal DT transfer functions as well as the loop transfer function and stability. So this is my digital voltage mode control loop, right, in digital. So this is my V naught, subtracting from V reference, V error, and then digital PID, because this is voltage mode PID controller, which is giving me my control voltage, and then modulator gain, which gives duty ratio to output. So this is control to output. That's why. So this is control to output. So I need GVD of Z. As you have mentioned, we use GVD, we require GVD of S to design controller in V0. So these are my small signal equations, right? So D perturb is what? A VM perturb by MCT. So say this is my RAM function and this is my VM. Say the slope of this is MC. So what is my duty ratio? So duty ratio is this part, right? So D perturb is nothing but VM perturb by MC into T. And MC into T, I am calling is 1 by MCT. So FM is what? 1 by MC into T. So I am defining it like that so that it will make my life easy. All the calculations will be easy. So I am defining it like that. So D perturb is FM into V perturb. And what is VM perturb? VM perturb is GC into V error, right? So let me use this area. So D perturb is FM into VM perturb, right? So D perturb is FM into VM perturb. What is VM perturb? VM perturb is GC into VE perturb. GC into VE perturb. And for the time being, say reference is constant. So this will be equal to 0. Then my VE perturb is minus V0, right? So FM into GC into minus V0 perturb. So again, V0 is what? C equivalent into XN, right? So I'll get minus GC minus GC FM C equivalent into XN perturb is my D perturb. So first I have drawn the closed loop diagram that I know. So I am getting this D perturb in terms of VM perturb, which is FM into VM perturb, and VM perturb is nothing but GC into V error perturb. For the time being, I'm considering reference to be 0 because it is a constant. And if you assume this to be 0, yes.
Yeah, this slope is different from emulator slope, or both are same?
No, this MC will be different from the emulated slope of current mode control. So whatever slope that you need, so accordingly we are considering MC.
Okay.
So then I got VM in terms of VE, which is GC into VE. VE is nothing but minus V0. So minus V0, and V0 is C equivalent into XN perturb. So now I can substitute this all the way in this first equation. So I'll get what? XN plus 1 perturb is equal to A equivalent minus GC FM C equivalent into XN perturb, right? This is my final expression. You agree? I think I have missed one B equivalent term also. So there will be one B equivalent term also here. So XN plus 1 perturb is A equivalent minus GC FM B equivalent C equivalent into XN perturb. All this into XN perturb. So now if you apply Z transform, you will get what? You will get this expression. So if you apply Z transform, you will get Z into X perturb of N is equal to, say this entire matrix is some X is equal to XN perturb, right? So my Zi minus X into XN perturb is equals to 0. Now, if I take the eigenvalues, I will get Zi minus X is equal to 0. And from this, I will get Z1, Z2, whatever values, and it should lie within the unit circle. So X, if I substitute back, X is A equivalent minus GC FM B equivalent C equivalent. So I have substituted. So how do I know the I dimension because A is 2 cross 2. So Z should be multiplied by identity matrix, which is 2 cross 2. So using from this, I will get a characteristic equation. Solving that, I will get poles of Z, and it should lie within my unit circle for the system to be stable. So this is how you check the stability in the digital domain. Now, what is my K loop? K loop is, let me change the color. So my K loop is GC of Z into FM into GVD of Z. So this is my K loop of Z. So if you want to draw the Bode plot, you will draw the Bode plot of this Z domain in such a way that it will have the necessary phase margin as well as bandwidth, and accordingly you will decide the controller. And you will decide the controller, and you have to check whether that controller is making the system stable or not, because you might be overcompensating and the system might not be stable. So you have to check between this as well as this. So one is the stability and the other one is the design. So for the designed controller, whether the system is stable or not, you have to check. So both are crucially important and we can check. So this point is clear, right? Up to this point.
Hello, that D perturb is minus GFM C equivalent H perturb.
Yes.
How it is substituted in Hn perturb?
So this D perturb is right there. So I have multiplied B equivalent into minus GC FM, C equivalent into Xn perturb, and GC FM are constant. So only B equivalent and C equivalent are matrix now. So GC B equivalent, C equivalent. One thing you have to be careful is the matrices. Constants are not a big deal. Matrices, I can write B equivalent into C equivalent. I cannot write C equivalent into B equivalent. Both are not same. So you have to be sure which is coming first and which is not coming. Constants, you can move it here and there because they are just constant without any dimension. So this is all about the digital voltage mode control. Now we'll go into the current mode control. So for voltage mode control, we got the stability equation and the loop transfer function. So what happens to the mixed signal current mode control? So in the voltage mode control, we are comparing it with the ramp. In the case of current mode control, say we are considering peak current mode control. So I will get reference current, and then this is my IL and this is my I reference. So I will check the stability, same what I have done, and the loop transfer function. So I will get one equation here and the other one equation here. So this is for the stability and this is for the design purpose. Okay, so first I have done what? I have got this small signal closed loop. So before I go into the mathematical aspect, I'll explain. So first I'm subtracting V reference minus V naught, which is giving me V error, and then it is going into sorry. So let me click the pen. So this is giving me V error voltage, which is going into PI controller, and that is giving me I reference. Sir, when this recording will be available? So by tomorrow night, so by Tuesday night, I'll be able to upload it in the YouTube video. So you can expect it by tomorrow evening before 8 p.m. I'll try to upload it. So and all the material will be uploaded by tomorrow night. So you can get all the PPTs PDF format by tomorrow night, and also the video will be available. Okay. So I reference and my duty ratio, you know, right? In the case of peak current mode control, how am I getting my duty ratio? So this is the duty ratio. This is my peak value. This is my value. So D perturb is nothing but peak value minus value by M1 into T, right? So from I reference, I have to subtract IL. So I am subtracting IL and then I am multiplying by M1T. So here FM is nothing but 1 by M1T. So that will give me my duty ratio perturb. Now from duty ratio, I have to get IL. How will I get? Control to current transfer function. And again, from duty ratio, I have to get V0. So I have to do control to output. So someone has pointed, here we need both the transfer functions. So both will be there. Will there be annotations too in PDFs? Yes. So every week I am uploading 2 PDFs. One is without annotations and one is with annotations. So if you do not want annotations, then you can like view the without annotations, and with annotations if you want to see all the details, you can have both. So both I'm uploading in the same link, so you can bookmark that link. So everyone, every week I'm uploading week 1, week 2, week 3, week 4. I'm uploading 2 PDFs. So this is all about the loop diagram. So now coming to my duty ratio perturbation, which is, as I have discussed, I reference minus IL by M1T, and FM is what? FM is my M1T. So this I have defined. So FM is I reference minus IL perturb. Now, how do I get I reference? I reference is again GC into V error, which is minus V naught. Again, there is less than a minute. So if this meeting is ended, please join it. So after this, we will be solving problem. So this is the like last slide. So after this slide, we'll go into the problem solving session. So GC into minus V naught is my I reference. So I reference is GC into minus V naught. And I know V naught is what? C equivalent into XN. GC into minus C equivalent into XN button. So that is what I am writing here. Minus GC into C equivalent into X button. So now there are two things. I need duty ratio, right? So I have to substitute this I reference here. What is my IL perturb? IL perturb is 10 into X perturb, right? So I got I reference in terms of X perturb as well as IL also in X perturb. So I substitute both of this in this equation. So till this point, is it clear? So where are we? So we got I reference in terms of X perturb as well as IL in terms of X perturb. So what is my D perturb? My D perturb is FM into minus GC C equivalent into X perturb minus 10 into X perturb. So this is my D perturb. So I have to substitute this D perturb back in my B equivalent. So IL is again 10 X perturb. So if I substitute my D perturb there, so what will I get? I'll get XN plus 1 perturb is equals to A equivalent into X perturb plus B equivalent into this, what is this? D perturb, right? So D perturb is FM GC into, so minus FM GC C equivalent minus 10 into X perturb. So if you do this, you will get Z. Again, you apply the Z transform. So the final expression I am writing, it is ZI minus A equivalent minus, so minus again will become plus, so plus B equivalent FM GC C equivalent plus B equivalent into 10. Again, this FM is there, so I think here there is FM. So here we will get FM into B equivalent. So there is, I think, no 2 will be there. So Z I2 cross 2 minus A equivalent. So again, as we have discussed, this is for the stability. So to check whether the system is stable or not, we have to find the eigenvalues, and then we have to ensure whether the system is stable or not. Now, coming to the loop transfer function. So there is one loop, right? So what is the loop transfer function of this? So if I make it a constant block, so what is this G? It will be FM by one plus FM GID. Am I correct? Because FM is the forward path and GID is the loop. So if I replace this loop, I'll get FM by 1 plus FM GID. So now what is my loop transfer function? My loop transfer function is this into GC into GVD. So that is what giving me loop. So using this, I will design my controller.
Hello, can you explain last part that?
Yes.
Loop
So I
transfer.
want this loop transfer function, but here there is another loop. So that loop is like this. So it is input is this, and here summer block and FM and D perturb, and then there is another here which is a GID. So if I want to replace this by a single D perturb with input, so what will be my loop transfer function? FM by 1 plus FM into GID, right? FM is forward, GID is feedback, and it is a negative feedback. So this is
Yes.
my forward. So now the loop transfer function is this into this into this. So FM by 1 plus FM GID into GVD into GC, which will give my K loop transfer function, which I will be using for
What?
controller design. So I again got two equations, one for stability and one for controller design. As you can see, this is the inner current loop. We have two loops. One is the inner current loop, and this is the outer voltage loop. So this is current loop control. So we have two loops. One is the inner current loop and outer voltage loop. So this is for mixed signal current mode control. For fully digital, we are not showing because it is beyond the course. So if you want to try, you can still try. So using these equations, some mathematical manipulation is needed. You can still do that. So, but we are not showing in this course. It is your interest. So this completes the. So just to summarize, we have started with small signal block diagram. So small signal block diagram. And then we have showed that there are two ways to do S domain as well as Z domain. And then from there, we moved into current loop stability. So some aspects of current loop stability we have discussed. And after that, we discussed the large signal DT model. And after large signal DT model, we have derived the small signal DT model by means of two ways, approach 1, approach 2. From the small signal model, we got small signal transfer functions. From the small signal transfer functions, we have done for digital voltage mode control as well as mixed signal current mode control. We got the stability as well as the loop transfer function. So to check the stability as well as the loop transfer function. So all these things we did in what domain? We did in we did in Z domain. So let me calculate. So all these things, whatever stability we got, everything is in Z domain. But for us, it would be difficult to do in Z domain. So, but we are mostly habituated to S domain, right? S domain, we can easily correlate, we can visualize and have a understanding about the pole location and everything. So we are more habituated to S domain. So in S domain, we have considered an continuous time with delay model. So continuous time with delay model we have considered. So this is my one model, and here we have Z domain discrete time model. So this is one thing and this is the other thing. So which one shall I use? Because this is more accurate. So this is more accurate. But this would be easy. I would say easy as well as we can imagine it. So this will be more easy to design the controller. So can I use this or should I use this? So that is what we are discussing with the model accuracy. So SAR has shown for control to output, which is GVD of S or GVD of S with delay and GVD of Z. So three case studies SAR has considered. So one is the discrete time continuous model. So discrete time continuous model is GVD of Z. Continuous time small signal model with delay is GV into e to the power minus S tau d, where tau d is the total delay, which is the sampling delay plus dBWM delay. And continuous time small signal model is GVD of S. So this is A, this is B, this is C. So coming to this is the gain plot, right? So this is the gain plot and this is the phase plot. So what is there in my gain plot? In my gain plot, so A, B, C are there. As you can see, this is what my non-red, so B and C. Can anyone tell why B and C are exactly matching? Hello, this and this. So they are GVD of S and GVD of S into e to the power minus S tau d. So they will only differ by phase. Magnitude will be same. So that's why they are exactly matching, and this is our DT model. Now coming to the phase. Phase, you can see this is completely deviating. So this is completely deviating. So I cannot use C. So whatever this blue dotted, I cannot use because it is not accurate. So I will not use this. So I will not use this because it is not accurate. Here it is closely matching until this point, but after that it is not closely matching. And if you see these two, they are okay. There is slight mismatch, but it is okay because it can be manageable. There is only slight phase difference, but it is okay to consider this much of error. So what is matching? The B is matching. So this is matching. So this is matching with this. So our conclusion is discrete time small signal model and continuous time small signal model with the delay are closely matching. There is some like some mismatch, but they're closely matching. So so when to use what? So this I can use for controller design because it would be easy to design a controller in S domain because we know it much easy and we can draw the board input, everything we can correlate easy. So we can use the controller design, so not delay, controller design using the continuous time with delay. But is this sufficient? No, it will not actually give us the entire stability of the system. So for stability, for nonlinear behavior, we use the discrete time model. So the final outline is like this. So I have two models. One is the discrete time small signal model, which I'll be using for stability criteria to design or study in depth. But if I want to design the controller, I'll use continuous time small signal model with delay. The delay is tau-d to make my life easy and to design the controller to have better understanding and everything. So this you will use for controller design, and but this is not sufficient to check the stability of the system because it is an approximate model and it fails to give the information about subharmonic oscillation, some nonlinear behavior. For that, we'll use with this. So we are using the best of the both worlds. So for stability, you have to use continuous time small signal model. For controller design, this is okay because we will be anyway designing FSW by 10, right? So this is FSW by 10. So in this region, so it will be close to this region and it is quite accurately matching. So the model is valid matching. So controller design, I'll use this, but it is not sufficient to check the stability. For stability, I'll go with the discrete time. So whatever stability equations that we got, so these should be used for my stability. But for controller design, you don't have to go with this. You can use the continuous time small signal model as we are going small signal based approach. So that is the overall outline. So we have discussed all the small signal model derivative transfer functions, everything. And in the final, we have seen whether our continuous time small signal model with delay can be used for controller design or not. Yes, it can be used, but for stability, you have to go with this method only, and this is not sufficient. And this is not matching at all. So because the delay we are not considering, and as you can see, the delay is significantly affecting in phase. So we are not considering this at all. So there is a trade-off between these two. One is easy to design control, and this one gives stability. This one fails to give me stability. So until this point, it is clear, right? Then we can go into the problem session. Hello.
Sir,
Yes.
sir, that discrete time model stability, we have to verify using eigenvalues.
Yes, using the eigenvalues, that mod z something something equal to 0. So you will find z values, and you have to ensure it is inside the unit circle. Then you can ensure the system is stable. Understood? Whoever is asking the question.
Yes, yes.
Okay. So now we are done with the theory. Let us move into the problem solving. So problem solving are completely dependent on the theory, as I always mention. So if you are very confident with the theory and if you are clear with the theory, then you can solve the problems easily, because whatever questions or problems that we will be making, that will be completely based on theory. So if you are very confident with the theory, then we can solve few problems. I think I have made some 4 or 5 problems. So to start with the 5. So what is phi. So xn plus 1 perturb is phi into xn perturb plus gamma into d perturb, right? So I am considering both initial and initial state perturbation and duty ratio perturbation. I am asking you gamma. So how do I do gamma? So I have to consider this region, right? So I will consider that region. So this is my xp, this is my x2, and this is my x1. So this is already discussed, but I am just revising it. So I got xd perturb as what? A1 minus A2 into xp plus b1 minus b2 into vin into d perturb t. But in the case of buck converter, I know a1 is equals to a2 and b1 is b1 and b2 is 0. So I can directly write xd perturb to be b1 into vin into t into d perturb. So my xd perturb is b1 into vin into t into d perturb. So this is my xd perturb, right? So from this xd perturb, I have to get this gamma d perturb. Now this becomes initial state perturbation. So initial state perturbation, I know xn plus 1 perturb is equal to e to the power a into time t into xn perturb. Now my gamma d perturb is e to the power a. What is the time period? T minus t on minus ts into xn or xn perturb, which is my xd perturb here. So that is b1 into v into t into d perturb. D perturb cancel. I know td is equal to t on plus ts. So let me change my color. So gamma is e to the power a into t minus td into b1 into v into t. So this is for again buck converter. So I have mentioned. So this is the buck converter, and both initial state and duty ratio perturbation I have asked, but I have only asked it for gamma. I am not asking phi. So what is the gamma in the expression? So this is my gamma. Is this question clear? Hello. How I am solving this? So this is based on small signal DT modeling. This I have discussed in today's lecture, so it is just similar question. Is this clear?
Sir.
Okay. So coming into the other part. So in this part is very easy. So here only initial state perturbation is given, and I have mentioned in my lectures that xn plus 1 perturb is e to the power at into xn perturb, as d perturb is equals to 0. So from xn perturb to this is x1 perturb, and this is x2 perturb, and this is xn plus 1 perturb. So I'll consider three equations. X1 perturb is e to the power a into what is the time period? Ts. So this time period is Ts, right? E to the power ats into xn perturb, and x2 perturb is e to the power a into what is this time? T on, right? E to the power a T on into x1 perturb, and xn plus 1 perturb is what? E to the power a, what is this time? T minus T on minus Ts. E to the power a T minus T on minus Ts into x2 perturb. So I have three set of equations. I have to do some manipulation. I have to substitute this here, and I have to substitute this here. Then I'll get what? Xn plus 1 perturb is equals to e to the power a T minus T on minus Ts, e to the power a T on, e to the power ats into xn perturb. Now if I substitute, or if I do the addition, I'll get e to the power at into xn perturb. So if I compare this with this, I'll get phi is equal to what? I'll get my phi is nothing but e to the power 8. So this we have derived in our lecture as well, but I have just showing it here so that we will be clear about all the calculations and concepts. So concept is very simple. From this point, we are calculating the next point. From that next point, we are calculating the next point. From that next point, we are calculating the next point. And then we are substituting, back substituting, and then we are manipulating to get the phi expression, which is also this. So if you do not change the phi, say if you consider the matrix here to be A2 and here to be A1 and here to be again A2, then we'll get this expression, because A2 into TS, the first part, and then A1 into T on, which is this part, and then we'll get A2 into T minus T on minus TS. But as it is a synchronous buck converter, A1 is equals to A2. So if you do that, we'll get phi is equal to e to the power 8. So until this problem, is it clear? Hello.
Yes, sir.
Okay. So now coming to the next problem. So next problem, I have asked you to derive what DT model using the approach 2. Approach 2 is what? Using the partial difference.
Can you show me the previous slide once more?
Okay, okay.
Okay, sir. Okay, sir. Please.
Okay, okay. So I am asking you to derive the small signal DT model using approach 2. So I have given the large signal model. I want the small signal model, which is xn plus 1 perturb is equal to something into xn perturb plus something else into t on perturb. So for xn perturb, for this constant, I have to differentiate it with xn. So the second term becomes 0. So I'll get dou by dou xn of e to the power at xn. So this is what? E to the power at into xn perturb. So this is my first expression. And for the next expression, I have to differentiate dou t on. So I'll multiply this. I'll get e to the power a into t minus ts minus e to the power a into t minus t on minus ts into a inverse into b1 into va. So if this one will be constant because it is independent of t on. So I'll get minus a t minus t on minus ts. Again, I have to differentiate the numerator. So I'll get minus a into a inverse into b1 into v. So minus a inverse a cancel. This minus will become plus. And t on minus ts, I know t tau d is equal to t on minus ts. So this entire expression will become a to the power t minus td into b1 into v1. So again, t on is what? T on is dt, right? So t on perturb is what? D perturb into t. So if I substitute that, I'll get t into d perturb. So my final expression, so it has two terms, a small signal one, so which is xn plus 1 perturb is equal to first expression e to the power at xn perturb. The second expression e to the power a t minus td b1 v t d perturb. So that is what we'll get. This is again.
Hello, can you explain that last step?
Last step. So
Dou by dou t on.
Yes, so t on we have, right? So dou f by dou t on I got. So I can write it as dou f by dou t on into t on perturb, right? So I got this expression, but t on perturb I know it is d into t. So t on perturb is d perturb into t. So instead of this t on perturb, I'll write d perturb into t. So I didn't get this part. So this was supposed to be t on perturb. But t on perturb is d perturb into t. So I have mentioned t into d perturb. So I have written in terms of xn as well as d perturb. If it was supposed to be t on perturb, then I'll get e to the power a t minus td b1 v in into t on perturb. Right. So that td perturb or t on perturb, depending upon what value you want it, you can change it by means of this equation. Is that clear? Okay. So coming to the problem 4, again we are going to the current loop stability. So current loop stability, we have discussed two things. One is mixed signal current mode control. Another one is the digital current mode control. In mixed signal current mode control, I have told that D should be less than 0.5. And in digital current mode control, I got MC to be greater than M1 plus M2, right? And only for the current loop stability, but outer current loop, like complete closed loop, it will be much more than this MC. But whatever we have considered, it says that at least the current loop is stable. Current loop is stable. I am not currently bothering about the overall stability. I have asked to find the small signal transfer function of IL perturb by I reference perturb. in our lecture, I have derived this, right? Az by z square minus z plus a is IL perturb by I reference perturb. So like if you want to go back, you can go back. There I have derived this. And I have defined A to be M1 plus M2 by MC. Now I have given what MC is 1.5 times M1 plus M2. So if I substitute that M1 plus M2 by 1.5 times M1 plus M2, I'll get A to be 2 by 3. You substitute that back here. So I'll get 2 by 3z by z square minus z plus 2 by 3. Understood? Until this point, how am I getting this? So it will give me IL perturb of z by I reference perturb of z is nothing but if I multiply by 3, I'll get 2z by 3z square minus 3z plus 2. So this is my final expression of the small signal transformation. So if you are not sure, let me go back where I have discussed this. So it is in the before small signal, before large signal tuning in the current loop stability. So here I have discussed, and so from here I am taking this. So this is the problem 4 from where I have taken. So I got the stability from the duty ratio expressions, and I have applied the Z transform. So from there I got this expression. So which I have used in my problem 4. So this is my problem 4. So I know this expression, and I also know the A. For finding the value of A, I have given you MC as 1.5 times M1 plus M2. Substituting that, you will get A first, and then again back substituting this, you will get this IL by I reference perturb. Now, if you want to check, you can check whether what are the roots of this equation, whether mod Z is less than 1. But without checking, I can say that it will lie in the unit circle. How? Because my MC is greater than M1 plus M2. So I know that the current loop is stable. So my roots should lie inside the unit circle. And this you can also check by calculating the Z. If you have calculator, you can quickly check the values, or maybe I can check 3 plus or minus square root of B square minus 4AC. 3 to 6, 4 is 24 by 2A. So you can check that, and it should lie within the unit circle. Because this is negative, I think it will lie in the unit circle. That you can check later. So with this, we complete our session. So if you have any doubts, you can ask, or let me summarize. If you want me to summarize, I can summarize. Or if you have any queries, you can ask.
Can you explain that small signal model for
this one? Or problem 3, which one? Hello, which problem?
third problem?
Okay. So in third problem, I have asked you to derive the small signal model using the approach to. Approach is what? Jacobian matrix or the partial fraction Taylor series expansion. So I have given you the large signal model. So this is the large signal model, LSM discrete time model. So large signal model discrete time. So from this, using this expression, we know that xn plus 1 perturb is dou f by dou xn into xn perturb, dou f by dou t1 into t1 perturb. So for the first part, this I need. So I have to differentiate it with xn, and the entire second term is independent of xn. So I have to differentiate only the first term. I got e to the power 80 into xn perturb. So I got this is e to the power 80. Now for the second term, I have to differentiate it with t1, and the first term is independent of t1. So only second term I have to differentiate. But for second term, I have multiplied this with this. So first term is again independent of t1. So this will be 0. And the second time I have multiplied, and then I got this expression. And t1 I want to represent in terms of d perturb. So t1 is d into t. So t1 perturb is d perturb into t. So because of that, we are getting this extra t term.
Okay.
So with that, we conclude this session. So we have discussed some model validation. Yes.
So in the fourth problem,
Yes.
if you find the roots, it is showing up.
If you find the roots,
the roots are 0.5 plus 0.645i.
0.5 plus.
You find.
Sorry, I think this is 2 into 3. B square minus 4AC by 2A. Have you calculated the values? this is 0.5
Yeah,
plus,
this is 0.5,
plus or minus
0.645
0.645
0.645.
J. So now you have to calculate the mod Z1 or mod Z2. So which is square root of 0.5 square plus 0.645 square. So 0.5 is 0.25, and this is, say, even if you take 0.7, it will be 0.49. So that will give us 0.74.
0.81.
So it is less than, I would say, 0.9. So it is less than 1. So it is lying inside the circuit. Got it. Actually, I have made a mistake. So it is 2a, b minus b plus or minus square root of b square by 4. Previously, I have ignored this 3 term because 3 is there. So either you can calculate this, or you can also directly tell from this, because we have got this expression from this roots only. So yeah, they are lying inside the unit circuit. Okay, then with that, we will conclude this session today. By tomorrow, I'll upload. So we have discussed about a small signal closed loop diagram, how to solve it in S domain, how to solve it in Z domain. And then we have discussed about the current loop stability of mixed signal current mode control, fully digital current mode control. And then I have shown the full digital current mode control MATLAB simulation. And then we have gone into large signal discrete time model. And then I have shown the validation using MATLAB. Then we have gone into the small signal DT model using approach 1, which is 5 gamma method, approach 2 Jacobian method. And after that, we have derived the small signal transfer functions, mainly the control to output as well as the control to current transfer function. Using the transfer function, we have got the stability as well as loop transfer function of digital voltage mode control as well as mixed signal current mode control. After that, we have seen the model accuracy, which model we will prefer for what, for our ease as well as stability, which model we prefer. And then we have solved few problems from the topics that we have discussed. So if you have no more question, I'll conclude this session here. So keep.
Okay, sir. Good night.
Okay, thanks. I'll end the meeting here.